As dusk settles over a dense suburban neighborhood, residents return home and immediately plug in their electric vehicles. This nightly routine creates clustered charging events, triggering localized power surges across residential grids. These simultaneous charging events shift the physical location of the electrical burden, changing the spatial stress profile of the distribution feeder minute by minute. The physical consequences of this sudden reactive power demand are measurable. Branch currents experience severe nonlinear spikes, which in turn force the nodes further downstream into sharp voltage sacks. Traditionally, utilities rely on statically placed capacitor banks to prop up voltages. But under variable EV loads, pockets of stress physically move along the feeder. A capacitor placed to solve yesterday's low-voltage node might end up pushing reactive current upstream and increasing system losses today. Mitigating these surges is a highly complex optimization problem, calculating exactly how to control the reactive flow across dozens of interconnected nodes. As modern distribution networks face dynamic, unpredictable EV charging loads, rigid deployment strategies become structurally inadequate. The hardware must be guided by algorithms that adapt to the load. To map a solution, we will look at a precise objective: optimizing the placement of exactly 3 fixed shunt capacitor banks within a radial network. The system will operate under a strict constraint. The total reactive compensation across all 3 banks is firmly capped at 2100 kV-ampere, or kVAR. Our testing environment is the IEEE 33-bus system. It's an industry-standard radial distribution network known for its long, high-impedance branches, which makes it highly sensitive to reactive flow imbalances. We will subject this network to 3 distinct operating states: an EV light condition at 75% load, a nominal EV base state at 100%, and an EV peak condition pushed to 125%. The question is whether a rigid budget of exactly 3 capacitors can be mathematically positioned to survive an escalating dynamic EV load profile. Finding the optimal setup is computationally brutal. Navigating the millions of possible capacitor locations and capacities requires running massive, time-consuming load flow equations for every single candidate. To perform this global search, the system deploys War Strategy Optimization, or WSO. It balances broad exploration with targeted refinement across the entire network landscape. The WSO algorithm continuously manipulates 6 specific variables: the physical bus locations for the 3 capacitors, and the precise kVAR injections assigned to each. To prevent computational bottlenecks, the framework embeds an efficiency engine inside the WSO, a ridge-regularized polynomial surrogate model. Rather than running a full equation every time, the surrogate acts as a local predictor. It evaluates promising configurations on the fly, drastically reducing the number of heavy load flow evaluations needed to find a valid solution. But the model doesn't replace the physics. Once the surrogate identifies the best candidates, the final solutions are rigorously verified using a stable backward-forward sweep load flow. This hybrid approach gives utilities the mathematical leverage to map the steep, nonlinear power losses of heavy EV loading without computational burnout. Let's look at the first test. The 75% EV light scenario simulates daytime operating hours when home charging penetration is at its lowest. The algorithm evaluates the network and clusters all 3 capacitor banks strictly at buses 27, 29, and 32, the extreme tail end of the feeder. The engineering logic here is straightforward. Under light loads, the upstream trunk has plenty of voltage margin. The reactive power shortages are entirely localized at the farthest nodes. This chart shows the real power loss over iterations. With the capacitors deployed at the tail, the active power loss collapses from nearly 110 kilowatts down to just 58.76 kilowatts. Looking at the initial versus final voltage profile, the deep trough seen in the uncompensated network is completely eliminated. The trajectory from bus 10 onward becomes remarkably flat. Under light load conditions, maximizing system efficiency strictly dictates that all reactive support must be concentrated at the feeder's most distant points. Moving to the 100% EV base scenario, we test the network under standard daily operations, without the clustered spikes of EV chargers. As demand rises, the physical placements change. The algorithm forcibly migrates the capacitors into a widely distributed stance at buses 1, 21, and 33. Placing a capacitor at bus 1, right at the substation, might seem redundant, but injecting reactive power at the very head of the system suppresses upstream branch currents enough to indirectly lift downstream voltages. This best power loss graph illustrates the stabilization. The optimized active power loss rapidly converges and settles at 122.52 kilowatts. The corresponding voltage profile plot confirms the strategy. The distributed placement triggers a uniform parallel upward shift of 0.02 to 0.03 per unit across the entire 33-bus corridor. As general demand reaches its nominal capacity, the system must abandon tail clustering. It trades localized support for balanced full corridor current suppression. Finally, the ultimate stress test. The 125% EV peak scenario simulates the massive power surge of evening EV fast-charging clusters. The baseline conditions here are severe. The initial active power loss reaches nearly 330 kilowatts, pulling the midsection buses into dangerously deep voltage drops. The algorithm counters with a radical adjustment, splitting the placements between buses 4, 16, and 32. The bulk of the power, 1350 kVAR, is stationed to guard the highly vulnerable tail at bus 32. But notice the secondary bank shifting far upstream to bus 4. This upstream capacitor acts as a vital choke point. It relieves the intense current load traveling straight through the main feeder trunk before it can cascade into downstream losses. This chart tracks the resulting drop in power loss. The bifurcated strategy slashes the active loss by nearly 140 kilowatts, bringing the final value down to 191.85 kilowatts. Checking the voltage profile plot, we see a noticeable flattening in the highly vulnerable 20 to 32 bus range. The optimization successfully limits the reactive burden introduced by the sudden EV demand. Surviving severe EV loading is an exercise in resource allocation. It demands a bifurcated strategy that splits compensation between route flow control and direct tail voltage support. Comparing all three stress tests reveals the macro pattern of the study. This tabular data tracks the method's results under different load conditions. By following the load variations, the algorithm secured massive efficiency gains, hitting up to a 46.45% reduction in real power loss. The data proves that optimal capacitor locations are never static. They must physically migrate across the network, as EV charging behavior pushes the system into different demand regimes. These system-level benefits were achieved strictly through reactive compensation, without injecting distributed generation or altering the physical feeder topology. Surrogate-assisted optimization provides a lightweight, highly efficient blueprint for utilities. It allows them to map, predict, and manage the spatial unpredictability of modern EV clusters using existing hardware. This study demonstrates EV-aware reactive power support, achieving up to 46.45% loss reduction and improved voltage profile through 3 optimally placed capacitor banks. For MATLAB simulation works, power system optimization, and research coding support, contact creativepublications2020@gmail.com.